Welcome to the lecture of Renewable Energy Systems. In today's lecture, we will discuss about the energy system control mechanism. We will further look into the renewable energy devices efficiency. For the successful operation of the network, it is essential to match the energy supply and demand either using conventional source or renewable sources. In this diagram, control mechanism of energy system is shown. The term energy system is often referred to an integrated demand and supply system. Several of the system relates also to developments of smart technology, which are being brought into utility supply of electricity from grid networks. Such smart technology is also important for autonomous system. The principles apply in some measures to suppliers of heat and fuel, but are immediately applicable to matching electricity supply and demand. As shown in this diagram, the two intervened circles, such as shown over here, are represented as an unstoppable current supply like renewable sources, since the energy in the environment flows whatever end the need. Symbol of two parallel line, such as this symbol, is like a voltage source battery, represents the finite source such as fossil fuel and nuclear power plant. The plus sign for positive feedback is being used, and the negative sign is for negative feedback is used. So here in the diagram, you can see this is the negative feedback system, and this is a positive feed forward system. Supply device means any equipment and system that extract energy from the source over here. And end use represent the device where the energy is consumed. Not all the energy can be utilized, so some energy may dissipate into the environment, which is represented here. In figure A, matching the demand efficiently to the renewable supply is important because the capital cost of the renewable generation is a dominant factor, and so the capacity and hence the cost of the generator should not be excessive. The energy flow, although essentially cost-free at source, needs to pass efficiently to the end demand. Therefore, the resistance to the energy flow at D, E, and F should be small. Reference to figure B, the negative feedback control from demand to supply is normal with fossil energy system. For example, in an automobile, the driver uses the accelerator to decrease the fuel supply if the vehicle speed is increasing too fast. It shows a negative relationship. For a renewable energy supply, a negative feedback, as in shown in figure C, results in potentially useful energy being wasted or split, such as shown over here. This is because renewable energy is a flow or current source in the environment that may only be diverted but not stopped. For example, a wind turbine operating at less than maximum capacity may produce more electricity than the load requires. Thus, controlling it negatively wastes the opportunity for more cost-free energy. In reference to figure D, another configuration to improve the utilization of renewable energy is using a feed-forward load management control system of the renewable energy supply, which split the services into high priority and low priority load, such as mentioned over here. The low priority loads are sized so that automatic adjustment will enable the total load to match the available supply at D at all times. Suitable load priorities load have storage capacity or will tolerate uninterruptible supply. The supplier encourages user to connect such load by offering electricity at reduced tariffs. This method is familiar as off-peak utility grid electricity, and as with some autonomous system such as the wind-based system and with some mini hydro system. An obvious way to match supplies and demand that have different dynamic characteristics is to incorporate storage devices as shown in figure E. In this way, energy will not be lost significantly. The great majority of renewable energy electricity generators are grid connected to utility networks. This includes microgenerators, so allowing immediate import when the microgenerator supply is insufficient to meet demand, and immediate export when there is more than sufficient generation. The result is to decouple local supply from local demand by so using the grid for both the export and import of energy. The grid becomes a virtual store. Moreover, there is still the benefit of having switchable load to optimize the on-site use of the microgeneration. This concept is shown in figure F. It seems obvious at first sight that technological devices should be efficient. However, this word means different things to different people about different technologies. The technical efficiency of an energy device usually means the useful energy supplied as a fraction of the input energy. By this definition, the best efficiencies of various common devices are as follows. Power station based on coal and oil has approximate 35% efficiency. In this efficiency only includes the direct generation of the source from the fossil fuel rather than reusing the rejected heat. The efficiency of gas turbine is approximately 45% and the nuclear energy has 35%. The efficiency of the car has approximately 10%. The cyclist while racing has approximate 7% efficiency. This efficiency is based on the rate of motivation energy, rate of food of metabolism. A regular cyclist over a year may have less than 1% efficiency. Electricity generator normally has up to 95% efficiency. The bicycle has approximate 85% efficiency and lights may have efficiency between 2.5% to 12%. It is clear that important common devices may have small efficiencies, but this does not prevent their use. For renewable energy devices, we start by using the same simple definition, that is, efficiency is equal to the useful energy supplied as a fraction of the input energy. Thus, hydroelectric power plants, including electricity to grid or initial potential energy of piped water onto the turbine rotor, has approximate 90% efficiency. Further, downstream water passes with very little energy as it drops away from the turbine into large open areas. Wind turbine in modern wind, that is the kinetic energy of unrestricted wind onto the rotor area has efficiency approximate 45%, but all the energy cannot be removed since the air must continue to move away downstream. Solar water heater at midday with clear sky and tank temperature initially cold gives efficiency of about 60%. Solar photovoltaic panel in the midday with clear sky has efficiency of approximate 17%. The wood burning stove and in-room flue pipe have about efficiency approximate 85%. Biogas burner efficiency is 90%, and biomass thermal power plant efficiency is approximate 30%. It is more important to assess the actual production of particular devices at specified site. Moreover, the environmental inputs are very variable. So the inputs are best averaged over time, usually a year. We need parameters that allow the annual production of a device to be assessed at particular site for which the term capacity factor or full load hours is used. The capacity factor can be defined as the ratio of energy delivered in a specified period and the energy deliverable at full capacity in that period. Normally, the specified period is 1 year, that is consist of approximate 365 days. In this case, the annual capacity factor can be defined as the ratio of energy delivered per year to the energy deliverable at maximum capacity per year. The full load hours is the ratio of energy delivered per year to the rated capacity. The value of these parameters for a device depends both upon its own efficiency and upon the climate at the site. Capacity factors are most frequently discussed in the case of electrical power generation, but the concept may be applied more widely. Note that solar devices can only capture sunshine in daytime. So if years include nighttime, then capacity factor is at most 50% even for a perfect device in an average day of 12 hours. Note also that values of capacity factor and full load hours are both independent of the capacity of the devices. So if their values for a particular site and technology are considered small, increased output may only be obtained by increasing the capacity of the installation. In addition, since the comparison is with the maximum capacity of device itself, these factors do not themselves give information about efficiency. They do, however, allow different devices of the same technology to be compared, either by type on the same site or by site with similar devices. Obviously, manufacturers and device owners try to maximize capacity factor and full load hour with values that approaches the theoretical maxima. But there are usually limitations owing to the particular technology and site and application. The resource potential of a renewable device is the energy it can supply per year. The resource may be estimated at any geographic scale from a household to the whole world. There are two common measures of resource potential in a geographical area. The first, the theoretical potential, is derived from natural and climatic parameters. For example, total solar radiation received on a continent surface. The theoretical potential is the upper limit of what may be produced from an energy resource based on physical principle and current scientific knowledge. It is the starting point from which apply restriction for siting, technical losses, environmental barrier, and etc. The second point is the technical potential. The technical potential is the amount of renewable energy output obtainable by the full implementation of demonstrated technologies or practices in a specified region. No explicit reference is made to cost, institutional policy, or other man-made barrier that may limit take-up of the technology. From the technical potential, more practical estimates can be made, allowing for other constraints, for example, avoiding sites of scientific or ecological value, prioritizing biomass for food use ahead of its use for energy, and applying cost limits. Harmful emissions may be classified as chemical, physical, and biological. Such pollution from energy systems is overwhelming, a result of using brown fuel, both fossil and nuclear power. Nuclear waste is example of brown fuel. This applies in particular to the greenhouse gases emission, which are a major cause of potentially dangerous climate change. Reducing greenhouse gas emission is one of the major driving forces behind the growing demand of renewable technology. Renewable energy is always extracted from flows of energy already compatible with the environment. The energy is then returned to the environment, so no thermal pollution can occur or anything but on a small scale. Likewise, material and chemical pollution in air, water, and garbage tend to be minimum. Environmental pollution does occur if brown energy is used for the materials and manufacture of the renewable energy devices, but this is small over the lifetime of the equipment and will decrease in proportion to the adoption of the renewable energy. The majority of the renewable technology produce significantly fewer conventional air and water pollutant than fossil fuel, but nevertheless impact upon the environment by being sited within large area of land as for example reservoir hydropower, which can also release methane from submerged vegetation and biofuel. Some renewables, especially wind power, do not interrupt the regular use of land for agriculture. In contrast, fossil fuel mining, especially from coal and uranium, has very negative impact upon the surrounding lands and in its use. There may also be some impact upon water resources. For example, limited water availability for cooling thermal power plants decrease their efficiency, which can affect plants operating on coal, biomass, gas, nuclear, and concentrating solar power. However, electricity production from wind and solar PV requires very little water compared to thermal conversion technologies and has no impact upon water quality. In today's lecture, we have discussed about the classification of resource potential analysis, pollution and environmental effects, and energy system control mechanism. Today's lectures end here. Thank you for listening.